So the aim of this video is just to give a short introduction to the motivation for developing Thermobar. Now, many of the fundamental questions in igneous petrology can be addressed using thermobarometry and hygrometry. For example, how hot was this magma chamber? What was its thermal history? Did thermal changes cause rejuvenation and eruption? How deep is this magma chamber stored? How does this relate to eruption triggering processes? Interpretation of geophysical signals during an episode of unrest? How wet was this magma chamber? Did high water contents trigger the eruption? Did volatile saturation occur just before eruption? Or how long did this magma chamber sit at depth? How quickly did it become rejuvenated? And as many of you know, many of these time proxies in magma chambers rely on an accurate temperature, so this links to thermometry. So there are many ways of calculating temperature, pressure and water contents using the composition of erupted minerals and liquid compositions. So for example, there's a wide variety of clinopyroxene barometers, so for example those of Keith Paterka in his 2008 review, more recently a machine learning technique by Maurizio Petrelli et al. We also have Amphibol, which can act as a thermometer and a barometer, so it can tell us pressure and temperature. There are also various expressions allowing amphibol compositions to be converted into equilibrium liquid compositions. And plagioclase is famously a thermometer and a hygrometer, so it can be used to get the temperature of the magma based on anorthite partitioning between the liquid and the plagioclase, and the water content of the magma. Now, as many of you know, there are already a variety of existing tools to perform these calculations. Keith Paterka on his website hosts a wide variety of spreadsheets which you can download for each phase. So here are some screenshots from his clinopyroxene spreadsheet. What you do as a user is you enter your liquid compositions here, you enter your clinopyroxene compositions here, and then you scroll along and he has various cells for calculations. So if you want to know what equation 33 returns, you'd find it here, etc. So you want to calculate amphibol pressures using Ridolfi 2021 barometer. You would download his Excel spreadsheet from his supplementary file. Again, you would enter your amphibol compositions here, and then you would scroll along to the relevant bits in the spreadsheet where it tells you the calculated temperature and pressure. Or if you want to use the Waters and Lang hygrometer, you can either download an Excel spreadsheet or they also provide a MATLAB script. Finally, if you want to use the machine learning barometer of Maurizio Petrelli, again you would go into the supplement and you would download this Python script which goes through it for a specific user input. And this is great that there are all these tools available, but the problem is they all have different input structures, so users must reorder their data many times. And they end up with an awful lot of Excel spreadsheets. If you're investigating a volcanic centre where you have amphibols, you have clinopyroxenes, you have plagioclases, you're going to end up with so many different places they're in. It's going to be hard to pull them all together and show them on the same plots. And you're just going to spend a lot of time, say you're flipping between amphibol barometers from Ridolfi and Keith Paterka, you'll end up dragging your column orders around quite a lot. Secondly, some of these rely on proprietary software. So for example, MATLAB tools, not everyone has access to MATLAB. Even Excel, using some of the free versions of Excel, causes problems when you're trying to iterate certain calculations with some of these tools. Finally, Excel doesn't really provide the advanced functionality that is required to address many thermobarometry questions. So for example, it's become quite popular in the literature to consider all possible matches between clinopyroxenes and liquids. And this is really because at the surface, in a lava, we get a whole host of crystal populations, many different clinopyroxenes. But on average, we only really get one liquid, the whole rock composition that's brought up. And that can be problematic to even characterise the composition of, say, due to olivine addition. So what has become more and more popular is to take all of sort of the liquids available for a volcanic centre or even a volcanic region and consider matches between those liquids and all possible clinopyroxenes, and then assess whether those matches are in equilibrium using a variety of equilibrium tests. The problem is this is very hard to do in Excel. You would have to hand line up every liquid with every clinopyroxene, and you end up with hundreds of thousands of rows very, very quickly. Now, David Neve addresses this in an R script, but it is not publicly available. And Scruggs and Paterka, there is a YouTube video showing how you can do this, a sort of adaptation of this in Excel, but again, it's relatively slow. So one of the things we've provided in Thermobar is a really quick function which allows you to assess these, apply different equilibrium filters, and the code runs very, very quickly within a matter of seconds. Another thing you might want to consider is, say we consider plagioclase liquid equilibrium. We know that plagioclase liquid thermometers are very, very sensitive to water content, and plagioclase liquid hygrometers are very, very sensitive to temperature. So for example, if you're using the Waters and Lang hygrometer, either their Excel spreadsheet or MATLAB, you have to know your temperature really well. But where are you going to get your temperature from? Well, maybe you'll get it from a plagioclase liquid thermometer, but that thermometer requires you to know your water content. So you could iterate by having Keith's spreadsheet up and the Waters and Lang spreadsheet, but it's just clunky. Whereas Python allows us to easily code up these sort of iterative problem solving solutions. So Thermobar is in Python, a rapidly growing open source language, which means anyone can access it regardless of how much money your institution has. It requires really minimal formatting from the author. All we ask people that want to use it to do is to input their major element data as oxides in weight %. And then they tell Thermobar what phase it is just by adding an underscore and then the phase identifier. So lic for liquid, underscore capital plag for plagioclase, CPX for clinopyroxene, etc. You can have any other columns you want which are available to you. So you can put in, say, your latitude, maybe pressure from melt inclusions. There is a way to quickly adjust the proportion of Fe3+ in your liquid, which can be used for assessing ion partitioning between different phases. Your column order, importantly, doesn't matter, so you don't have to arrange these columns in a certain order. You can just have any of them in any place as long as they have these headings. And we've coded up more than 100 popular thermobarometers and hygrometers, involving equilibrium for just liquid, olivine and liquid, olivine spinel, various pyroxene, so clinopyroxene liquid, clinopyroxene only, orthopyroxene liquid, 2-pyroxene, as well as various amphibole, plagioclase and feldspar and 2-feldspar thermobarometers.